Now we expand our knowledge of what we've just seen for RC, RL, RLC circuits and what happens with the resonance within those circuits. And what they specifically become is something that we call a filter, in this case, a passive filter, since we're dealing with passive devices, RL and C. So we're going to look at four different types of passive filters. We'll start off with the low pass, move to the high pass, the band pass, and then the band stop. So we'll analyze the operation of the different types, RC and RL in the low pass case, RC and RL in the high pass case, and then the operation of the band pass and the band stop filters. Some terms that you need to become familiar with then are low pass filter, high pass filter, band pass filter, band stop filter. What is the pass band and what is the critical frequency? We've got F sub R here. That could be F sub C actually. Roll off, attenuation. What is a decade when we start talking about the Bodie plot terms? And then what is the center frequency? So a low pass filter allows signals with lower frequencies to pass from the input to the output while rejecting higher frequencies. This type of scheme or technology is really useful in the area of audio, where you are trying to filter certain frequencies. Your bass speaker, you want to pass all of the bass frequencies, but you want to stop all of the higher and mid-range frequencies. So this will be the fundamentals of what goes on when you are talking about filtering in your audio systems. You can see below the block diagram for a low pass filter, V in, V out, and then you can see the representation of what happens with the frequency versus the output in a signal as it's being processed by the filter. So a general response curve then in B for the low pass filter, as you can see what's happening as the frequency increases, the voltage out decreases down to some minimum. The range of frequencies passed by a filter within a specified limits then is called the pass band of a filter. The point considered to be the upper end of the pass band is at the critical frequency. And we can see that right there at the bend here, where we are at the difference between passing and rejecting the signal. The critical frequency then is the frequency at which the filter's output is at 70.7% of the maximum. You can see here that's 0.707 of the voltage in. The filter's critical frequency is also called the cutoff frequency, the break frequency, or the minus 3 dB frequency, because the output voltage is down 3 dB from its maximum at this frequency. The term dB or decibel is a commonly used unit in filter measurements, and we'll get into describing what that's all about. So a decibel is a logarithmic measurement of the ratio of one power to another, or one voltage to another, which can be used to express the input to output relationship of the filter. The basis for the decibel unit stems from the logarithmic response of the human ear to the intensity of sound. For those of you that have taken the first semester physics course, towards the end of the course, you'll get into that specific area of study. The decibel is a logarithmic measurement of the ratio of one power to another, or a voltage to another. So we can see here the following equation expresses a power ratio in decibel. So a decibel then is equal to 10 times the log of the ratio of the power out to the power in. From the properties of logarithms, the following decimal formula for a voltage ratio then is derived. And you can see now we have 20 times the log of V out over V in. So let's take a look at how we develop that. So if we start off with the first, dB is equal to 10 times the log of the power out over the power in, and we define the power just by the power law. In this case, we want voltage squared divided by R, so V squared over R as a voltage, as a power out and power in definitions. Now we're going to do a substitution into the first equation. So instead of having the ratio of power out over power in, now we have 10 times the log of V squared out over R over V squared in over R. The R's cancel out and we're left with V squared out divided by V squared in. Because we have a square in the numerator and the denominator, we can factor the denominator or the exponent 2 out of both of them at the same time. And then by doing a manipulation, the 2 then becomes a factor for increasing this now to 20 times the log of voltage out over voltage in. So you can see we can come up with a decimal relationship based on power in and power out, or voltage out or voltage in. So if we look at an example, at a certain frequency, the output voltage of a filter is 5 volts and the input is 10 volts. We want to express the voltage ratio in decibels. So we choose the second one. 20 times the log of V out over V in gives us 20 times the log of V out, 5 volts out, 10 volts in, which is 20 times the log of 0.5. Again, pull out your calculator, enter 0.5, hit your log key on your calculator, you'll get a value, multiply that times 20, and we end up with minus 6.02 dB then as the decibel relation for that power ratio. So the first set of circuits we're going to look at are the IRC low pass filters, then we will move to the RL low pass filters. And so we can see as we look at this, we're back to using our relationships for X sub C and FC. In this case, we're going to use this schematic to do some problems, to do some solutions here, analysis. So when we come back, we'll take a look at this in depth.